We're in Geometry Mod 3, Topic 1, Lesson 3, Activity 2, 478. To be ready for this video and for this page, it's actually like a rather long one, so we're going to take it slowly in that 478 will directly tell us what to do on page 479, but I want to go through something you're going to need to know on this one. So to be ready, 478 is not going to have a lot of writing on it. An extra sheet of paper is going to be the thing that's going to have a lot of writing on it. And then we're going to use both of these together in the next video to do page 479. So here we go. Consider the given statement and diagram to prove that a bisector of an angle divides the opposite side into two segments whose lengths are proportional to the lengths of the sides adjacent to the angle. Wow. That's a lot of language. Bisector of an angle divides the opposite side into segments whose lengths are proportional to the lengths of the sides adjacent the angle. So maybe some highlight is the appropriate thing just to kind of understand this given, prove, and diagram. And we're going to do some stuff here as well, but just kind of talk about this right now. Given AD, so that's in the middle, use the red for this one, is bisecting BAC. Prove AB over AC is equal to BD over CD. Okay, so some blue and some yellow. Blue and yellow. Okay, A. We have some more to do, but I'm just trying to process what's on this paper as well. Draw an auxiliary line. What is an auxiliary line? An auxiliary line is a line or line segment added to a diagram to help in solving the problem or proving a concept. Okay, all right. So we're going to draw an auxiliary line that's parallel to AB. So not right there. Because it's through point C, so it is over here. Then extend AD. So there's AD. We're going to extend it so that it intersects the auxiliary. We're making similar triangles. I know about this. Okay, so maybe the way to do this, just by kind of like eyeballing it, is positioning one edge of the protractor and then slowly, without trying to twist it, over to there. So then, yeah, these two edges mostly look parallel. Maybe a little bit. Yeah, maybe like that. I'm going to use a pencil so I can erase. If I extend this, do those look parallel? Pretty close. Okay, maybe like off by like a degree or half a degree or so. They'll eventually meet because, you know, human made them. But at least there it is. And then I can ink in this. I can ink in this much right here and right here. And then it says label the point of intersection E. Something that I know right now, because parallel lines cut by a transversal, parallel lines cut by a transversal will have congruent alternate interior angles. So this angle here will be the same as that one. That's just me thinking out loud, thinking ahead. Now, what I'm going to do is I'm going to prove that the two fractions of blue to blue are equal to yellow to yellow. Well, let's see. I'm going to kind of like bring out the scratch paper now, and we're going to do this in the form of a flow proof. And in the form of a flow proof, you start with a bubble that has the given in it. AD bisects angle BAC. That's given. Bubble it. Okay, what else is happening? We did part A to draw an auxiliary line. So the way that we drew the auxiliary line is also creating this. CE is parallel to AB because that's how I created it. I did it by construction. Okay, so some other things. This is all like setup right now. All of these are the top of the flow proof diagram. What else? Okay, I have this vocab word here, and the word being bisect actually does tell me something. To bisect means to cut in half, and the angle being cut in half is angle BAC. So angle BAC is going to be cut into two angles. Angle BAD And it's going to be congruent to angle... CAD. Oh, and I got to put the word bisect with it. Angle bisect. Can you see that? You can't even see that. There you go. Sorry. Okay. It's a definition of it. What else we got here? Okay, this one. Because of alternate interior angles, angle BA, oh, by the way, this is an arrow connecting there. The word bisect is used down there, so you got to connect them. I'm kind of trying to keep my diagram in place. Maybe like that. Is that good enough? Maybe like that. Okay. So with the parallel lines, and I said it out loud, it's time to write it down. Parallel lines create congruent angles. So angle bad is going to be, well, they use BAE. I think maybe I'll use one of the two. Is going to be congruent to angle CEA. Because they're alternate interior angles, and there's a theorem on it that we talked about in the entire last trimester. So these are going to draw together. Okay. What else do we have here? We have EAC. Oh, interesting. Okay, so BAD, so that angle, and CAD, that angle, these two can be brought together. They can be brought together because this angle and this one are also the same. So I can say, see. Let me get this one that I need to say it. So I'm going to say angle CAD is congruent. So this angle is CAD. And it's going to be congruent to angle CEA. You know, if you bring both of these statements together, they both have bad in common. So we can bring them together. The process that does that is substitution. So we're going to, well, they say transitive property on the next page. I'm looking ahead, by the way. I'm a little underneath, like, transparency. I'm looking at the two-column proof, but I want to make the flow proof match that. So by the transitive property, which is substitution in another way of connecting it. Okay? So these two boxes that have bad in it, and they're equal to CAD and CEA, well, that means CAD and CEA must be equal, because they're both equal to bad. Angle, bad. Okay? But then that means that these two angles here are base angles of an isosceles triangle. ACE is isosceles. So this means triangle, and I'm going to put this in red. I'm going to put this in red for a reason you'll see in the next video. That means triangle ACE is isosceles, because there are two congruent base angles. Which ones are they? Those, CAD and CEA. Okay. Since this is an isosceles triangle, then that must mean this line segment AC and this line segment CE have to be the same, because two sides of an isosceles triangle must be congruent. AC and CE are congruent. They are sides, what's the word that I want to use? Yeah, I'll just say it this way. Sides of an isosceles triangle theorem. Okay, so what have I got so far? You're just kind of following. Thank you for following along the way. I'll zoom out and show everything all at once as well. So if you've skipped ahead, that's fine. You have the triangle. We have the angles that match. We have these lines and these lines that match. Somehow we got to get into BA and BD. Okay, let's see here. AC and CEC are there. Yeah, that's true. These, I guess, are equal to each other, right? AC equals CE, showing it on the screen, because of the definition of congruent segments. Okay, flow-proof style. What else? What else? This angle here, BCE, this is a parallel. This is a parallel, like a triangle cut by transversals. So parallel sides cut by transversal create alternate interior angles that are congruent. So angle BCE, yeah, where would that go? Angle BCE, just leave it. Angle BCE is congruent to angle CBA, or they say, let's go alphabetical, ABC. And this is because they're alternate interior angles. And it's a theorem. In fact, all of this box happens because it's connected, all the way back up in the parallel sides box. And so through it all, this is also part of the problem. So you know, like when you're doing these Matthew problems, like you see them like cross over each other. It's important to kind of tease the boxes apart so you can see the lines that connect across from one to the next. Then that must mean that angle DAB, that's a typo, triangle DAB is similar to triangle DEC by angle similarity theorem. Box it. And so the angles that I'm specifically talking about is this angle, the ones that are blue, shared by both triangles, and let's see here, this angle up above. Let's see here, this goes. Yep, we're going back up to this one, angle BAD and angle CEA. Those are similar, so make sure I'm connecting the correct thing. Wait. It is this one. Okay. Okay, that comes down to there. All the way like that. Zoom it out if I can. Not very well. There's a lot going on. Okay, two more, right? Two more. So in the two more, once we know we have similar triangles, then, and the similar triangle is like not in the original shape. It's like we extended this out to make an isosceles triangle here, and that gives us the similar shape. Now what we get to say, because of similar triangles, is that there are matching sides. So I'm going to use my blue highlighter again, going back with the blue highlighter. Apparently, CE and CA are the same length. So way back up above, when we're supposed to, I'm looking right here, we're supposed to compare in this relationship. That's a bow tie relationship. We've seen this diagram in the past where the small triangle is similar to the big triangle. We had to create it. It wasn't there originally. So in order to finish this whole thing out, because these two triangles are similar, we get to say the proportion of the sides. I'm going to go blue to blue and yellow to yellow. We get to say this, that, get my letters in here, AB over CE is equal to BD over CD. And right now, I'm still pushing towards the proof. I have this highlighted yellow, and I have this highlighted blue. So something is missing. But the reason this is true is by similar triangles, corresponding sides. I'm going to need more paper. Oh, my word. There's so much going on here. Here's more paper. By corresponding sides. Oh, my gosh. Of similar triangles are proportional. All of this box now happens from there. Now, then last of all, if we remember way back up here that AC and CE were both statements about being blue, then that means that we can substitute CE with AC. Yo, that's the bottom of the proved fraction that we're missing. So this box will push towards, with the help of the box up above it, coming all the way in, coming in for their one, AB over AC equals BD over CD. That's blue. That's yellow. That's the prove, and it's by substitution. Oh my good Lord, good word. Okay, here we go. So let's look at the entire thing. This is the flow proof minus like where the paper split. We're trying to get over everything. So camera come up. Whoo. It's like a lot. 1, 2, 3, 4, 5, 6 doesn't count. 7, 8, 9, 10, 11, 12 steps in order to show a theorem, which will be in angle bisectors, we have proportional sides. And we're going to make fractions out of them and solve them. I'm going to terminate the video here. Click 479 because that's where we're going to take all of our flow proof and put it into a 2-column proof. So thank you so much for watching. See you in the next episode.